Begin recording. Perfect. So yesterday we worked on stoichiometry, and stoichiometry really is centered around a balanced chemical equation, a balanced chemical reaction, whatever you want to say there. At the heart of a balanced chemical equation, you could always think about it as a recipe. Um, this many of this reactant will react with this many of this reactant. So, you know, 2A react perfectly with 2B to form 3C. That would be an example of a reactant, of a balanced chemical reaction. Um, and then stoichiometry is really the question of, okay, well, when you have this sort of golden rule, this sort of hypothetical perfect ratio, that's great. But what happens when you have 326 of A and 14 of B? Stoichiometry asks you the question, how much are you going to make? It also asks you, well, what's going to remain after this reaction has taken place? And that's when we get into the idea of the excess reagent and limiting reagent. I think that it's really helpful to always think about, a recipe of sorts, like I use the example of a cheese sandwich. You could also use like an Oreo cookie, uh, something a little bit maybe more appetizing than a cheese sandwich. And then you know what it consists of, and then you just have to think, okay, well, I have 25 chocolate wafers. How many of the like cream discs do I have to make the Oreo cookie? Okay, well, if I have 25 of the crackers, um, 25 cookies plus 15 um, cream inserts. How many cookies will I make? Well, let's see. 25 cookies. That gives me the opportunity to make a grand total of 12 because an Oreo is what I'm thinking of here consists of two cookies. So I can make 12 cookies. Do I have enough cream inserts? I do. I've got 15 of them. So I'll be able to make 12 Oreos just fine. What's going to be left over? Well, there's going to be one cookie and three inserts. So I think that, that in a nutshell is what stoichiometry is. And I think that anytime that you can take a complicated idea and a balanced chemical reaction and just rephrase it and basically take the symbols that I provide you with and convert those to symbols that you're familiar with, it's going to help you out a whole lot. Um, so in addition to that, you have to be able to convert from mass of a substance to moles of a substance, and then find that that balanced chemical reaction shows a molar relationship. 2 moles of A react with 2 moles of B to produce 3 moles of C. Okay, well, what if you have 65 grams of A and 345 grams of B? Well, you have to come up with the molar mass of those two different substances. So if there's one slide that I'd say, hey, spend a lot of time on this slide, it would be this one. Because this slide, in conjunction with your periodic table, is going to help you answer so many different questions. Now, we ended yesterday's class talking about making solutions. And what I'm going to try to do is try to put this in the context of making Kool-Aid. Just because I feel like that's, there's a visual component to it, but there's also like a flavor component to it. And, I think most folks have made Kool-Aid or, made Gatorade, we'll say. And you know that when you add too much water, well, that Gatorade or that Kool-Aid just, to put it bluntly, is not as flavorful. And that's because the concentration of it has gone down. It has been diluted, or it is more dilute. So we're going to look at calculations on how to make make like the ideal flavor. Um, sorry. Okay. So when we talked about concentrations and when we talk about and chemists talk about concentrations, they talk about this unit of molarity. Molarity is the measure of moles of a solute in liters of a solution. Okay, so if you have 3 moles of something in 1 liter, that would make a 3 molar solution. If you had 3 moles of a solute in 0.5 liters, could anyone add to the chat what that concentration would be? In this one, it's quick and easy to plug it into or to try to mental math it, but plug it into your calculator. 3 divided by 0.5. 3 divided by 2 would be 1.5. 6. And that's the sort of math question that you're like, I know how to do this. And then you do it and you're like, wait, oh, stop right there. Okay, oopsies. So when you compare this solution and this hypothetical solution, what's the difference between solutions A and B? The volume. Okay. Add a Y or an N to the chat. A Y if you agree, and N if you don't understand. For solutions A and B, add a Y to the chat if you agree that they both have the same number of moles of solute. Okay. Now, I'm going to give you a visual of these two. So let's say that X, 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 that would be our 3 moles. We'll just come up with something simple like that. And here is 1 liter. Okay. Now that would be B. Add a Y or an N to the chat if you understand that. Now, to draw solution A, well, what's the difference between these two? The volume of solution A is 0.5 liters, so the volume is less. Do we have the same number of moles? We absolutely do. Okay, so tell me between solutions A and B, if you were to drink solution A or solution B, and let's pick something like it was well, which one of these two is going to be stronger when you drink it? A. You know, one little sip, one strawful, one spoonful, whatever, of solution A is going to be very strong. It's going to be very rich compared to B. So we use this calculation to communicate that this is more concentrated because there are the same number of moles, but in less space, in a smaller volume. Give me a Y or an N if you understand that.
Busybody C.
Great. Okay. So I think that I think when it comes to solutions, it's sometimes helpful to think about Gatorade or like making your own Gatorade from the powder. I don't know if anyone's ever done that. Or Kool-Aid, making it again from the powder. Trying to visualize that and think about, okay, well, how much have I added to what volume? And what does that mean? Does that make it stronger? Does that make it weaker? I think that's a helpful thing to consider. Now, when it comes to This sort of, or okay, this sort of thing. What is the molarity of a solution made by dissolving 10 grams of NaCl in enough water to produce 1 liter of solution? Okay, tell me Y or N, is this the correct calculation? I picked my solute, 10 grams of NaCl. That's supposed to be a G. Well, you're right, DDA. That's absolutely right. That is not correct. It has to be in moles. You are completely right. So what I really want to do is I want to take the mass that I've been told, and I need the molar mass. Now, just as a little bit of an aside, if you have this slide deck open, you can follow this link to a periodic table. But I also know that the molar mass for sodium chloride is 58.5. And that's not because I've memorized the periodic table or anything of that nature, but just NaCl is used as an example so frequently that it's kind of committed to memory for me. So what I'm going to do is I'm going to say 10 divided by my molar mass, 58.5. DDA, I'm taking your number there, and that looks about right. So 0.17 moles. Okay, so then I'll take 1.17 and I'll divide that by 1 liter, and that would be 0.17 moles. Now tell me what letter corresponds to what is probably the best answer for this. A, absolutely. So that's what I'd want you to mark there. Okay, now can you give me a Y or an N in chat? A Y if you understand, an N if you don't follow what we did. Okay, great. Now, this next slide is one that we looked at yesterday. This is where we kind of went through the visual process of making a solution. In order to make a solution, one of the key elements is that you have to be very precise. You have to be very specific. And that's kind of the nature of chemistry and biochemistry and science in general. You have to be very precise with the amounts. So in this case, somebody measured out 1.2 grams of copper sulfate. Now, I'm going to use my phone here to pull up the molar mass of copper sulfate, CuSO4 mass, molar mass. CuSO4 molar mass, that is 159.61 grams per mole. Give me a Y or an N if you believe me. Good. Yeah. You have no reason to not believe me. So I'm happy that you trust me. And you can trust me, or I'd like you to trust me. Um, okay, so 159, just have to make, that looks worse. 159.61 grams per mole. We have 1.2 grams. So tell me, in terms of a mole, more, less, exactly. Do we have more than a mole? Do we have less than a mole? Or do we have exactly 1 mole if we have 1.2 grams? DDA, you're right. We have less than a mole. We have a lot less than a mole. In order to figure out the specific number of moles, we're going to do 1.2 divided by 159.61. So use that as your kind of like, if you're, I remember hearing this term, computational thinking, and it's a way of thinking. It's a way of like, okay, when I get this information, what do I do? What is the next actionable step that I do? When you are asked about preparing a solution, you need the mass that's provided in the question or in the scenario. 1.2 grams. And you are going to divide that by the mass of the substance in question, or the molar mass of the substance in question. So 1.2 divided by 159.61. DDA gives us 0.0075. I'm going to give a bonus point to the entire class if somebody can convert that number to scientific notation within the first two responses. So be careful and please don't use any outside resources, just your own head resource. Okay, we got times 10 to the negative third. Oh, is it negative third or positive third? The good thing is you guys covered all your bases. One of those, let's see, one, two, three decimal places. So you're right on the exponent, but is it DDA? Yep, yep. You guys actually colluded very well and covered all your bases by, it's like, is it A or is it B? Well, it's A and it's B. So, but you're absolutely right, Sparrow and DDA. It's 7.5 times 10 to the negative third. Why is it to the negative? Well, because the number that we had was in complete notation or full notation, and we converted it to scientific notation. So when we move the decimal place 1, 2, 3 spots, we moved it to the right, so we got a negative. I also like to think about it as when I'm going from full notation to scientific, my arrow goes like that. And for some reason, I always just think right pointing arrow is a negative. So long story short, 7.5 times 10 to the negative third. Okay. Now the question is, what is the concentration? Well, the concentration is based on the moles, which we've calculated. This is our moles of our solute and the volume of our solution. Can somebody tell me what's the volume of our solution? And that would be in exactly 100 milliliters. Great job. Thank you, DDA. Now, what has our solution volume been in all of our other samples or all of our other calculations? Has it been 100 milliliters? And my furrowed brow in question indicates no, it hasn't. You're absolutely right, DDA. It's been 1,000 milliliters or 1 liter. So we need to make an adjustment. And here's what we're going to do. We're going to say, after we've got our moles, we're going to say 7.5 times 10 to the negative third divided by, let's look back. Liter of solution. Can somebody tell me what 100 milliliters is in liters? And that's a little bit tricky, but would you, well, I like to say it's tricky, but then you just show me the answer super fast, so it must not be tricky, and I respect that. But one way that I always think about it in the event that you're struggling with this at all, 100 versus 1,000. This number is 10% of this number. 10%. Whenever I think of 10%, I always think of money. So 10% of a dollar would be $0.1. And that's, I'm just sharing how my brain works there. Another thing you could do is 10 divide or 1,000 or 100 divided by 1,000, and you'd end up with this 0.1. So then we'd take 7.5 times 10 to the negative third divided by 0.1, and what we would get is 0.075. Perfect. Well done, DDA. Okay. Now this series of pictures shows the process. And this might seem a little bit strange. It might seem like, well, that seems excessive, but the way that I want you to visualize this is think about it like this. Let's think on a large scale. If you went to, let's say that you had um, the largest pot in your kitchen, if you got that and you filled it all the way up to the brim, and you're like, I'm going to make a stew. And so what I want to do is I am going to fill this all the way up to the top, and then I'm going to add like 4 cups of salt. Add a Y or an N to the chat if you agree that the salt will dissolve in that water. Yeah, no doubt about it. The salt will dissolve in the water. Now, when you've got that pot with water all the way up to the brim, if you add, like a little pinch of salt, do you think the water is going to spill over? Y or an N? And yeah, no, I don't think so either. If you add 2 pinches, same thing. It's probably not going to spill over. But let's say that rather than a measuring cup, you just got a glass and you filled it all the way up to the brim with salt. And you took that salt, knowing that the salt dissolves, and you poured it in. What's going to happen to the water level in that pot? Remember, it's filled all the way up to the brim. It's going to rise. And eventually, since it's at the brim, it's going to spill out. Does everyone agree with that? Y or N? Yeah. So what I want you to take away from this is that even though something dissolves, and in the case of sodium chloride, salt, even though it dissociates, it separates into a sodium ion and a chloride ion, even though that happens, those ions still take up space. And so they're going to go into that solution, and that water is going to spill out. Now, my point in bringing this all up is that is important, or that's an important thing whenever it comes to making a solution. You have to do it very deliberately. You add the solid. So you weigh out your solid, the 1.2 grams of copper sulfate. We throw it in here. Okay, great. Then we add some water. And then we swirl that solution. Notice the water level here is lower than this etched glass line. That etched glass line is the important point where, well, we can't go above that because if we go above that, we have more than 100 milliliters of solution in there. So we added a little bit of water, and then here's my drawing of swirling. Swirl, 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 swirl. So you mix the solution up. So that copper sulfate goes into solution here. Now, where I've put that big asterisk there, are we done? Add a Y or an N to the chat. Mm-mm. Follow-up question. Has our solid dissolved and dissociated? Chances are strong it has. So at this point, that copper sulfate has gone into solution. And we see that right here. Does that make sense? Add a Y or an N to the chat. Okay. So then if we stopped right here where I'm putting a big X, and I know that I have X's all over, well, on this slide, I'm actually not too bad. If we stopped right here, do we know the volume that we have added? We don't. Because this piece of glassware, this volumetric flask, is a piece of glassware that, it's good for one thing. And that one thing is measuring exactly 100 milliliters. If the solution level is below that etched line, all that you can say is, well, it's less than 100 mils. If the solution level is above that etched line, well, it's more than 100 milliliters. But if it's right here, if somebody came along and was like, oh, that's 394.6 milliliters, and you're like, huh? If somebody said that that was 396.4 396 point 39.6 milliliters, you'd be like, you have no basis for that. Does that make sense? Y or N to the chat? Okay. So that's why, yes. So we are adding water all the way up to here at that point. Now, this is a tricky question. This is like a next level sort of question, but I think you guys are up for it. Okay. In here is 100 milliliters of Solution. Okay, in that solution, we have copper ions and sulfate ions. We've also got H2O. Does everyone follow that? Add a wire and into the chat. Okay. So now in here, is there 100 milliliters of H2O? Add a wire and into the chat. Yes. High five. Wonderful. That's one of the most important principles of understanding how to prepare a solution. If you understand that, like, I know that one of the things I struggled with whenever I learned this was I was always like, and then I use this to make a solution. I'd be like, oh yeah, just add 100 milliliters of water because that's what I want. No, it's not. The solution volume will be 100 milliliters. Will you add close, in here, do you add close to 100 milliliters of water? Yeah, you get close to it. I wouldn't be surprised if you used 98.9 milliliters of water, just under 100 milliliters. But you do not use 100 milliliters of water because this copper sulfate, those ions, or when they go into solution, they occupy space. And so that's one of the important parts about like the logistics of making a solution. Okay, now we're going to jump ahead to this right here. This is all about preparing a what's known as a dilute solution. Um, and one of the ways that I think about this is like, let's say that let's say that you are the director at a kid's summer camp. And you're like, okay, we need to make, um, I need to make, let's see, we'll just put simple numbers. Let's go with, we've got 50 kids, and what I need is 10 of those big Gatorade, um, buckets. Let's see, what's the word that I'm looking for? Not troughs, the things that they throw on the coaches after the Super Bowl. Um, Coolers, yeah, that works. The ones with the spout. Okay. Okay, so I need 10 of those. And all these 50 kids, I've got my numbers. If I have 10 of those, then basically each one of those coolers serves 5 kids. Okay, that's a good ratio. Now, let's imagine that, we want all those kids to, when they go to those coolers, to taste Gatorade and be like, yeah, this tastes like Gatorade. Each one of those things. So that, if we have cooler one, two, three, a kid who goes to cooler one and then goes to cooler two, if they get Gatorade from one and then two, it effectively tastes the same. Does everyone follow me there with this maybe unnecessarily lengthy scenario? Wire it into the chat if you follow. Okay. Now you might be thinking, wow, this is a very disordered system. And you're probably right, which is an indication that I probably should not go into logistics and supply chain management. But here we go. We've got these 10 coolers, and we want all of them to have the exact same taste. So what we're going to do is we're going to make one, we'll call it a super mix. And this super mix is going to be super concentrated. So what I mean by that is basically for this super concentrated super mix, let's say that it's, 5 liters. And that 5 liters, we've got, let's just imagine that we got like 120 packets of or of Gatorade and dumped them in there. Just a randomly large number. Is everyone following me there? Wire it into the chat. Okay. So what we're going to do is we're going to take a small amount from each one of them, or sorry, a small amount from this super mix and add it to each of my 10 coolers. Does everyone follow that? Okay. Now, this equation right here, M1V1 equals M2V2, also known as C1V1 equals C2V2, gives you the guidance on what to do. So let's say that we've got 5 liters in here, and let's say that we take 100 milliliters and put it in this first cooler. And then I'm going to label the coolers 1, 2, 3, 4, 5. And then someone else comes along and they get 100 milliliters for cooler 2, 100 milliliters for cooler 3, 100 milliliters for cooler 4, and then somebody else takes over and they get confused and they take 50 milliliters and put it in cooler number 5. Okay. Now, all of these right now, all of the coolers 1 through 5, all that they have in there is the 50 or 100 milliliters from the super concentrated mega mix. Does everyone follow that? Add a wire and into the chat. If you follow that, then you'd agree that, well, they should all taste the exact same because all that has been added is something from that super concentrated mix. Now, what's going to happen though is someone else is going to come along and to each one of these, they're going to add to each one 900 milliliters of H2O. And yeah, they'll stir them up and everything like that. But let's say that you went to cooler number 1 and then 2 and then 3. Are they all going to taste the exact same? 1, 2, then 3. Yeah. What if you went to 1, 2, and then 5? Are they all going to taste, or maybe not taste, but are they going to be equally as intense? No, they're not. Which one's going to be the weakest one? Five. You're absolutely right. Because that one has the least of our original solution. Okay. Now, we can quantify this. And what we can do is let's say that our original solution here, so this super concentrated mix, let's say that it was 3 molar. Let's just go ahead and say that it's 3 molar Kool-Aid. We're going to say that is our M1. Okay, so this M1 information is our starting stuff. Add a wire and into the chat if you understand and follow that. Okay, so now the M2 V2 stuff is all about, well, your endpoint. And what I mean by that is, what about these other solutions that you make? So our endpoint there. Now, what that means is I'm going to do the calculation for solutions 1 through 4, because those are all the same. What I'm going to do is I'm going to take my concentration, my M, my molarity, and I'm going to say 3 molar. And then I'm going to take the volume. But 1 through 4, what I'm doing is I'm taking the volume that I removed from this super concentrated solution. So what volume should I put right here to multiply by 3m? Zero 0.1 liters, or yeah, in this case, you could actually say 100 milliliters because we're going to be consistent with our volumes. But I like what you guys are doing, so I'm going to stick with zero 0.1 liters. Now I'm going to set that equal to my endpoint. My endpoint, do I know my concentration? I do not. But what I do know, so I'm going to put an M2 here. What I do know is what is the volume of this solution? Well, the volume is the total volume, let me say, is 100 milliliters plus 900 milliliters, also known as 1 liter. So I'm going to say 3 times 0.1. And I'm going to kind of continue this calculation. I'm going to say 3 times 0.1 is 0.3. That is equal to M2, 1 liter. Divide each side by 1, and I get M2 equals 0.3 molar. Okay, so that is the concentration for solutions 1 through 4. Now for solution number 5, the 5 liters does not matter. Thank you for asking. That was basically just a way of saying, hey, we've got more than enough to work with. Um, so answer me this. Is the concentration of solution number 5 going to be higher or lower than 0.3 molar? You're right. Okay. Let's go ahead and plug that calculation in. 3 molar times 0.05, because it was 50 milliliters, equals M2 times, and that would be, our total volume here is different. It's not 1,000. Our total volume is going to be 50 plus 900, which is 950 or 0.95. So 3 times 0.05 is going to be 0.15 equals M2 times 0.95. Divide each side by 0.95. 0.15 divided by 0.95. Yep. DDA strikes again. Well done. M2 is equal to 0.158. Now that's a little bit not concerning, but that's a little bit like, oh, I kind of, my first instinct was to say, oh, well, I added half the volume. I added half as many moles. I did. But whenever I did that, my total volume was reduced. That's why the answer is not 0.15. Okay, so next up is a percent calculation. If you've ever bought hydrogen peroxide, H2O2, for like if you get a cut or something like that, some people pour hydrogen peroxide on it, or rubbing alcohol, 70%, or this is even true with like um, alcoholic beverages, like beers sometimes are like 5.4%, or in like states like Oklahoma and Utah, I think that the beer is not, I don't think it's like above 3.5%. I can't remember. And that has to do with the alcohol content in that beer. And those states regulate it different than other states. But anyway, percent by volume. and percent by mass is what that's looking at. Essentially, rubbing alcohol. This isopropyl alcohol or isopropanol is a liquid, but it's a liquid mixed with water, in which case the solute is a liquid. The solution, the total solution, is also a liquid. It is a mixture. So what you do for this is you take, well, let's say that we made 150 milliliters of isopropanol and had a total solution volume that was 700, or no, let's see, it says 473 milliliters on the bottle. So we have our volume of our solute and the volume of our solution. So we take 150 and divide it by 473. 150 divided by 473. Nope, 73. Times 100 to make it a percentage. And we get 31.7%. Okay, that is the scenario when you're dealing with a solute that is a liquid. So the way that you would see this in a question would be something like, hey, oh, that's a great question. So it does not. Now, what you have to do though, and what I did but didn't explicitly say, is I matched my units. So I matched this 150 milliliters versus the 473. I matched the milliliters over milliliters. If this bottle right here didn't say 473 milliliters, but instead was like 1.05 liters, then I would have to convert this 1.05 liters to 1,050 milliliters. So that's what I would have to do. And the answer is that's a fantastic question, DDA. This does not have to be in liters because we're reporting this in percentages. So that's why if anyone's ever heard of Everclear, Everclear is an alcohol that's or it's a liquor that I think is 180 proof. And if you've ever looked on a liquor bottle or ever seen or heard of a liquor bottle mention proof, that has to do with the alcohol content. And Everclear is something like 180 proof. That is measured on a scale out of 200 total. So essentially what that means is, well, divide 180 by 200 and you get 90%. So anytime someone's like, hey, I'm going to drink some Everclear, say, that's not a good idea because essentially what they're drinking is 90% alcohol or 90% ethanol. And like I said a moment ago, most beers are like 5.4% roughly, or 5 to 6%. Um, Drinking like a small amount of Everclear is drinking like, I don't know, like 16 beers at once. And thank you, Sparrow. Yes, yes. It's just it's kind of a safety thing. And yes, that might sound not exciting, but it's like a safety thing. If you ever go somewhere and someone's like, hey, we got this awesome punch, there's Everclear in there, and be like, oh, is this like in a bucket? Is this in like a trash can? And then they're like, yeah, awesome. Then you say, I have this kind of rule in life, and so far it's done me pretty well. Don't drink things out of trash cans. Um, I don't know. It's just this thing that I came up with. Um, at any rate, it's potentially hazardous. When I was in high school, there was a kid, I was a freshman in high school, and there was a pizza place in my hometown that bands would play at. And that was really cool for high school kids. We could go and watch bands and not get in trouble. And then someone had a bottle of Everclear in their car and they like snuck it into the pizza place and they drank it. And then the pizza place couldn't have bands anymore. Or they decided to not have bands because as it turns out, high school kids were drinking Everclear in the parking lot or in the bathroom. I don't know where it was. But either way, this kid ended up going to the hospital because he had way, way, way too much alcohol in his system in a very, very short period of time. Okay, so then that's by volume. Substances like hydrogen peroxide, well, this is going to be mass of a solute versus mass of a solution. Same sort of thing. You have to match the units. So this is, let's say that you have 125 grams of your solute, and let's say that our solution is 1,097 grams. Well, then you do 125 divided by 1097, and you would get 0.113947,129. Multiply that by 100, and you get this is 11.39%. Okay. So more times than not, chemists talk about solutions in molarity, but it's still also important to understand them in the context of percentages, because that's something that's a little bit more common that you encounter, not necessarily on a day-to-day life, but that you might see more often. And it's good to be aware of that. Okay, so is there a point we'll have to convert grams to milliliters or vice versa? That's a great question. And the only way that you can do that is, and the only way that you can accurately do that is with when you know the density. Um, does anyone add a number to the chat if you have a digital balance, like a food scale? I've got one in my kitchen, and sometimes I'm like, I'll track my calories and track what I'm ingesting. So I'll get a glass and I'll put it on there and I'll add milk or something like that. And it will tell me, okay, well, this was 125 grams. And I'll be like, okay. And then I'll toggle it over to uh, volume and it'll say 125 milliliters. Well, that's actually wrong. The reason is because that's using a conversion or using the density of milk of water, not milk. Milk is probably going to be a little bit more dense than water just by virtue of sugars being in there and with proteins being in there. So it's and fats because as I've gotten older, I've transitioned to drinking whole milk. I grew up on skim milk and it was gross, especially now that I've tried whole milk. Um, but anyway, that to answer your question, I don't believe so just because in order to do that correctly, you have to have the density of the substance. So it's not a direct conversion. Um, but that's a great question. Okay, so now what we're going to do is we are on to the second to last chunk of material. I have posted the material for Wednesday after our exam. Wednesday will be a regular office hours day. And then during our regular class period, I'll be available for office hours. But Wednesday's a pre-recorded lecture also. I've posted that. That stuff will not be on this exam on Tuesday, but it will be on the final, which is on Friday. Now, taking that into consideration, this is the last chunk of material that is on our exam on Tuesday, because Monday we'll do a review. I'll go through practice problems, give you a rundown of what to expect on the test. And we'll work through that. But this is something that it's 33 slides, but I'm going to kind of touch on some slides a lot more than others. So we are talking about acids and bases and pH. Now, can anyone give me a number or numbers associated with a pH scale if they've ever taken a chemistry class before? What are some important numbers that stand out from a pH scale and, what's the significance of them? Feel free to add them if you remember them. So acids, Okay. So you are correct, but with a starting point of 7. So the pH scale ranges from 0 to 14. And what that means is that a pH of 7 is neutral. Above 7 is basic. Below 7 is acidic. Now, thinking about that, there are lots of things that you consume on a daily basis that are acidic, and then there's things that are basic. And then there are lots of things that, if you look right here, this is a Diet Dr. Pepper can, and there we go. Let's see, we got carbonated water, caramel color, which I'd always like to taste the Diet Dr. Pepper without any coloring in it. Um, Aspartame, that item on the second line, phosphoric acid, Diet Dr. Pepper. And actually, okay, I have this right here. These are pH strips, and these strips will tell me how acidic something is. So, um, I'm going to do two things. One, okay, and the way that this is read, this is a pH strip that is color sensitive. And if you look down here, I'm going to put the top back on so they don't all spill out all over my desk. So we've got a pH scale 0, 1, 2, 3, 4, 5, 6, 7, and then 7, 8, 9, 10, 11, 12, 13, 14. So if I am in a basic solution, an extremely basic solution, it should look like this. So this right here should look like that. If it's acidic, if it's extremely acidic, the color pattern will look like this. Now, I'm going to do my saliva. And what I see is it's pretty darn neutral. And it might take a little bit for that to develop. Uh, but now I'm going to try. I just finished my coffee. Let's go with 3, 2, 1. Diet Dr. Pepper. Okay. Okay. Diet Dr. Pepper with a pH strip. It's pretty acidic. It's about a roughly a 4. So that's fairly acidic. And you know what? I'm gonna drink this, and I'm not the pH of my mouth is not going to change very much. The pH of anything in my body is not going to change very much by that Diet Dr. Pepper because phosphoric acid or that acid is not going to do a whole lot, and your human beings are resilient. Okay. Now, with that in mind, this is where we are. We're at item 7. Now, when you think of acids and bases, chances are you might think of household chemicals. Household chemicals like Windex, vinegar, muriatic acid. And I know you're probably not like muriatic, or you might be like muriatic acid. Who's thinking of muriatic acid? Well, as it turns out, there's lots of acids that are household chemicals. Vinegar is probably the most accessible and common acid. Vitamin C is an acid. It's ascorbic acid. Windex has ammonia, which is a base, and Drano is sodium hydroxide, which is a strong base. Now, acids that we're familiar with, well, they can have a taste. They're going to be typically fairly sour. They're going to dissolve active metals, and they will react with a base to form water and salt. Now, bases by comparison, well, they have a bitter taste to them. Whenever I think about acids and bases and like flavorings and things that I've consumed, um, one of the things that crosses my mind is, has anyone ever had like an airhead or not an airhead, warheads? That's what they're called. Or a Sour Patch Kid or something like that. Well, that flavoring is just some sort of acid or a base and the balance of those. So when you think about like ingesting that, all that that's doing is causing some physiological response within your mouth to be like, ugh, ugh, it's tart. Oh, that's awful. That's super basic, is what it is. So imagine if you got that and you like dissolved it in water. Chances are it would show up as a basic solution. Bases most commonly, when you get them on your hands, your fingers, they feel very slippery. Now, that's a little bit of a warning sign. Like if you're working with a base and you get it, and you don't realize this, but part of you feels a little bit slippery. You need to put your hand under water and let it run to dilute that and wash that away. So that slippery feeling is almost it. Don't take that as like, oh, that's no big deal. It's just a slippery feeling. Instead, you should be like, ooh, that means I have a base. Because what's going to follow that slippery feeling is a burn. Bases will react with acids to form a water and a base. Now, can anyone tell me what it's called whenever you add a base to an acid? My suggestion and my hint is it starts with an N and it ends with an neutralization. Like whenever you get if you were to spill an acid, what you want to do is, from a biggest safety concern is you want to dilute it away. You want to wash it away. But in the right setting, in the right scenario, if it's controlled, if you have an acid spill, add a base to it and you can neutralize that acid because that's what the base will do. Which is why some people like, advice when it comes to oh, what is it? Like there are some things what is when you eat really, really hot chicken wings, for example, what is the drink that people are supposed to consume? Milk. Why is that? Well, that flavoring agent that has that very strong, intense heat, that's an acid. And what do you think milk is? Yeah, you're neutralizing it. Milk is a base. So you're adding milk to it to basically cancel it out. Um, Now there's a lot going on there because, there are some times whenever you eat something that's spicy and you're like, you start crying and then you touch your eyes and then you're like, oh my gosh, what have I done? But at the end of the day, that's all acid-based chemistry. Now, or that's mostly acid-based chemistry. Now, when it comes to identifying acids and bases, I showed you guys this sort of litmus paper. This is pH, or sorry, this sort of pH paper. This pH paper is very precise. This will, give you this color pattern and this color scheme that you can use to detect if something is acidic or basic. This gives the entire range. This sort of paper, I'm going to scribble out the right-hand side. There is also litmus paper that is blue or it is pink. And whenever you take that blue litmus paper and you dip it into one type of solution, it will change to pink. And whenever you take a red or pink litmus paper and dip it into a solution, it will give you a blue appearance. So you use blue litmus paper to detect acids. You use red litmus paper to detect bases. Blue litmus paper, blue litmus paper turns pink whenever you put it in an acid. What do you think happens whenever you take blue litmus paper and you put it in a base? Nothing. It stays blue. What do you think happens whenever you take red litmus paper and put that into an acid? Red litmus paper in an acid does not change either. Red litmus paper detects base. It doesn't do anything when you put it in an acid. Okay. Now, a metal will dissolve. It will begin to kind of blow up like this and create a lot of bubbles, and that's what you're going to see. Now, there are theories on acids and bases, and what I mean by that is this is kind of like definitions. There's an Arrhenius acid, and there's also Bronsted-Lowry acids and bases. What I want you guys to do is to think about acids and bases using the Bronsted-Lowry idea, and actually kind of both of them. But if you were to go around with a definition of a Bronsted-Lowry acid and base, that's going to put you in a good place. A Bronsted-Lowry acid has a proton to release, and a Bronsted-Lowry base can accept a proton. Now, with that said, an older definition of an acid and a base, and it's older, and I think that it's like an easy intro, is an acid produces a proton and a base produces a hydroxide ion. So whenever you see something like this, HCl versus NaOH, before you say anything, I want you to look at these and I want you to know that these are both ionic compounds. Now, these two ionic compounds will both in water dissociate. Which one of these, whenever it dissociates, will dissociate and make an OH or a hydroxide ion? Which one of these will make a hydroxide ion? And whenever I say that, we're starting from this or we're starting from this. Sparrow, you're absolutely right. NaOH will make a hydroxide ion because this will split off into Na plus and OH minus. HCl, by comparison, an ionic compound that will dissociate into H plus and Cl minus. Now, there's a possibility that you're looking at this and you're thinking, but why won't this NaOH split into NaO and H plus? Why not? Well, the reason for that is because a hydroxide ion is a polyatomic ion. And that's a polyatomic ion that you need to know. And whenever you see OH, think about that as, okay, that thing is going to come off by itself. So let me ask you, do you think that KOH is an acid or a base? Add it to the chat. Okay. What about MgOH2? Acid or base? Okay. What about HOH? You got a base? Okay. What is HOH also known as? H2O. HOH is also water. Now I only gave you this because you guys got this and you got this. HOH, also known as water, can act as an acid or a base. So if you said base, I didn't say it was wrong. But what I want to show you is whenever this splits off to give you that hydroxide ion, so when this kind of in solution goes off to OH minus, what's left behind? H plus, a proton. So HOH both makes a proton ion or a hydrogen ion, but it also makes a hydroxide ion. So that makes water kind of not trustworthy. Now, with that said, if you start out with the idea that if you can pick off a hydrogen ion, that's an acid. If you can pick off a hydroxide ion, that's a base. That's going to put you in a really good place. Now, what we have, however, is this molecule down here, NH3. When NH3 is in water, what's going to happen is that NH3 has this lone pairs of electron or that lone pair of electrons. And what that's going to do is that's going to pick off a hydrogen ion because this can act as a base. So it can accept a proton. It doesn't have a hydroxide ion, but it accepts a proton. Okay, so if this acts as a base, then and this gets this hydrogen, what's left behind? If you have HOH and you take away the H, what's left behind? OH. So if NH3 is acting as a base to make NH4, then what is water acting as? One thing acts as an acid, or one thing acts as a base. What does the other thing act as? An acid. And this kind of goes back to, well, this whole thing gave up a hydrogen ion. So this is an acid, and NH3 is a base. Okay, now th those definitions are good to know. Um, can something can something accept a hydrogen ion? If the answer is yes, then it's a base. Can something donate a hydrogen ion? If the answer is yes, then it is an acid. Here we have our pH scale of some, common things that you see and things that you don't. Okay, so I've got my two pH strips. I'm gonna go ahead and look at my pH strip for my cola once again. No, that's my saliva. That's still at about a 7, so that's good. Good, bad, whatever, it doesn't really matter. Then my I think that the cola ended up being right at about a 4 or 5. Because when you look at this strip, it's again a little bit complicated. Oh, dang it. We've got all of the colors there. So on this side, it's a little bit up here, but then this one on the far left closest to this finger is a little bit lower. So it's a little bit complicated of a kind of code to read. But at any rate, so my data right now conflicts with this right here, this cola drink. But I think that this soda, hmm, it's a little bit flat. So that would probably have a little bit of an influence on the pH because its flatness is related to the CO2 that's dissolved in there, the carbonation. Okay, but there are fruits that are acidic, oranges, tomatoes. Then seawater is a little bit basic. Milk of magnesia, household ammonia. The entire spectrum ranges from 0 to 14. If something is exactly pH of 7, it's neutral. If it's above that, it's basic. If it's below, that's acidic. Blood is about pH of 7.5. You do not want your pH of your blood to drop. But the good thing is that your body has a mechanism to prevent that from happening. If anyone is ever in diabetic ketoacidosis or DKA is what it's commonly known as, then they're having a pretty extreme diabetic event, in which case they will look like they're, and I'm going to use the technical term, they will look like and communicate and act like they're in an altered state. So it's almost like sometimes it will display as if somebody's drunk or something like that, but in reality, that's not what's going on. Instead, they have they have very high blood ketone levels, in which case their blood is slightly acidic. And it's not like acidic like 5, it's acidic like 7.2. But that change, it might even not even be that much, but that's enough to cause some pretty substantial differences in physiology. Okay, now when it comes to calculating pH, all that we care about is hydrogen ion concentration. Now, this function in your calculator is the negative log function. In order to calculate the pH of something, you take negative log and then that hydrogen ion concentration. And the good thing is that this is on a log scale. We can use something like this. So when we look at this specific example, a solution with a hydrogen ion concentration of 0.001 molar has a pH of. Now I'm going to show you how to solve this question without even using your calculator. We're going to go through process of elimination, however, to do that. Okay, the pH scale ranges from what to what? I'll give you the high end. It can be all the way up to 14. What's the lowest pH? 1, 0, pretty much. Yeah. Okay. Now, your hydrogen ion concentration. That would be 0.001 moles per liter. Okay. Now, that's good to know, that sort of calculation conversion thing. We can eliminate C because we know that our pH scale ranges from 0 to 14. What does that mean for A, B, and D? Well, those are all still possible. And if we look at those different options, there's elements of them that make them all appealing. For example, A. Well, that's tempting because, well, there's a 1 there. I mean, if I was in a pinch, I might be like, oh, well, let's go with 1 because I see 1 there. I like it. Um, but then if we look at answer option D, well, 0.001, well, this is 0.001. That's also tempting because those numbers are the same. Now, B, that's a little bit confusing. That's a little bit like, I don't know why that one's tempting. But let me show you this. 1, 2, 3. We moved our decimal 3 places. And this is a logarithmic scale. And I got to tell you guys, that's the right answer. So if I were to, and just to give you some other ideas of how to navigate these sorts of questions, let's say that I had H plus, hydrogen ion concentration of 0.01. What's the pH of that solution? 2. 1, 2. What about, actually, what about this? Yeah, this would be pH equals 0. Now, let me tell you, one of the things that's important to understand about pH is you're rarely, if ever, going to have a solution with a hydrogen ion concentration of 1. So you're not going to have 1 mole of hydrogen ions per liter. And in your body, you're also not going to. So that's something to kind of consider there. Now, the questions that I want you guys to be able to navigate relate to this. How many decimal places do you move it? Which pH is going to be higher? Solution A here or B? Higher pH. Solution A has a pH of 0.003 and solution B is 0.01. Which is going to give you the higher pH? Yeah. 1, 2, 3. So that's pH of 3. And that 3 happens to, it would be 3 point something. This is 1, 2. Okay. Now, tell me which solution is more acidic, A or B? B. That's great. That's the sort of question that people always get frustrated and stumped by because they're like, wait a minute, is it as the hydrogen ion concentration goes up, that means it's more acidic. When the hydrogen ion concentration goes up, the pH goes down, right? Or is it the other way around? So keep those things straight. Now, you can do a pH measurement with red cabbage juice. By squeezing the heck out of a red cabbage, you can basically get all these different colors based on different concentrations of that red cabbage juice. Now, what I want to talk to you about here is I want to go ahead and dig deeper into acids and bases, not just conceptually, but what are their names? When we look at this list right here, common acids and bases. Common base, sodium hydroxide, hydrochloric acid. Those two are examples of strong acids. Now, here are, let me go ahead. I'm just going to go here. No, I'm going to show you tables, a pair of tables. I like this table, and this is one that really just blew my mind for the longest time. I remember as a student in my first chemistry class in high school, um, struggling with this like heck. And then whenever I took chemistry again in college, struggling with this like heck. And here's the thing. This is a list of strong acids. Just like muscular strength, this is on a spectrum. Who is the strongest person in the world? Name their or add their name to the chat. I think it's I'm gonna go with the Incredible Hulk. He's the strongest. Okay, The Rock, yeah. Yeah. And of course, this is really opening the door for an argument and discussion like, oh, well, I think it's this person because they ran a marathon carrying a rock. Or this person ran a marathon carrying the rock. So that's why they're the strongest. The rock couldn't do that. Um, but this is quantifiable. This is your list of strong acids. HCl, HBr, HI, HNO3, H2SO4, HClO4, HClO3. Um, then let me tell you this, acetic acid is also an acid. Is that a strong acid? Answer Y or N in the chat. Let me rephrase that. Is acetic acid on the list of strong acids that I've provided? No. So, is acetic acid, is that a strong acid? It's not. If an acid is not one of these, it is not considered a strong acid. Same thing goes with your strong bases. If it is not in this list, it is not a strong base. So I mentioned that H2O acts as an acid and as a base. Would you classify it as a strong acid or a strong base? No, it's neither. Can it act as an acid and can it act as a base? Yes, it can. But is it good at either of them? Not particularly. So, what I want you to know about acids and bases is these two lists are the extent of it. If it is not, if an acid is mentioned and it's not one of these, it is a weak acid. If it is a base and it is not listed in this list, it is a weak base. That's important because what this boils down to in terms of acid and base strength is, and this is kind of the last point for today, HCl. We've got A and B. Tell me, is A strong acid? Add a Y or an N to the chat. Great. What about B? Is that a strong acid? Is it a strong base? No. B is a weak acid. And that weak acid is acetic acid. Now, I know that I mentioned previously, oh, well, when you see OH, think base. I stand by that, but I want you to understand that this is all on a spectrum. CH2C, C2H3COOH is acetic acid. It is a weak acid. Now, your definition for a strong acid and a weak acid, or your definitions for acid strength, you might think, oh, well, if it's, a strong acid can dissolve anything. A tempting answer, but that's not correct. A strong acid has to do with whenever you put this into water, what happens to it? If you had 100 molecules of HCl and you added it to water, you would get 100 hydrogen ions and 100 chloride ions. Does everyone follow that? Add a Y or an N to the chat. Okay. Now I want to put that in contrast to this C2H3COOH. I'm going to underline the hydrogen that is kind of lost, that's donated. This is a weak acid. Again, let's go with 100 of these molecules. So the model is that this molecule, C2H3COOH, will split up into C2H3COO minus and a hydrogen ion. Does everyone follow that dissociation? Add a Y or an N to the chat. Okay. Now, because this is a weak acid, when you put it into solution, what you get is the following. Let's say that you get, or what you would get is something like this. 5 hydrogen ions. Okay, so of those 100 molecules, we get 5 hydrogen ions. Then we get 5 C2H3COO minuses. Then we get C2H3COOH. How many of these are left? Tempted close, close. Remember these two things kind of pair up. These are what I'm underlining right now are the dissociation products. So from one of these, you get one of these and one of these. So if you end up with five of these and five of these, 95. Great job, Ryan. Because only five of the 100 C2H3COOHs will break up. 95 of them will remain intact. It's always tempting and tricky to look at those numbers and try to track it. But what this is showing, and I'm going to erase this over here. What this is showing you is that a strong acid, or what I want you to take away from this is when you talk about a strong acid, every single one of those molecules dissociates. Add a Y or an N to the chat if you understand that. When it comes to a weak acid, which I'll just label WA, not every single one of them will dissociate. Some of them will, but not every single one of them. Okay, that's where we're going to stop with this. There might be some details on this topic that I touch on Monday, but Monday is largely going to be reserved for review. If you have any questions over the weekend, please don't hesitate to contact me. Other than that, though, I want to thank you guys for coming to class, and I want to say I hope that you have a great weekend. I will get this recording posted a little bit later. Your practice exam for exam number 3 will be up a little bit later today as well. I've got to do some finishing touches on that. And other than that, have a good one, everyone. Thank you very much for coming to class. See y'all.